Hello, welcome to another video session for OAE 5053 VLSI Systems Design. In modern front-end digital systems design, we are used to building our digital circuits out of logic gates, and we're used to thinking about these logic gates as performing a logic operation. You put in a set of voltage inputs, logic 1, logic 0, you will get the outputs after a certain amount of propagation delay. And we're used to designing and thinking about these circuits as having this propagation delay. However, in the real VLSI systems, the real IC, that is integrated circuit that is fabricated, this delay is only an average specification, because in the process of manufacturing VLSI integrated circuits, we will tend to our manufacturing process, our fabrication process is not perfect, so there will be deviations, slight differences in the actual fabrication of the geometric structures, and there are also differences and deviations in the operating conditions in which we operate our integrated circuit, namely the voltage that is applied and the temperature that is applied. Now, in the early years of VLSI integrated systems design, when we were building circuits at 100 microns, 1 micron, these concerns weren't so important, because the variations in fabrication, the variations in voltage and operating temperature wasn't as wasn't a significant portion, wasn't as large as the actual operating voltage and the lengths themselves. But as we've tried to make transistors operate faster and faster, we scale them down, meaning we reduce their dimensions, and once we reduce the dimensions, we reduce the operating voltage, we find that the effect of variations in manufacturing and operating conditions actually start to play a bigger and bigger role. That is, they contribute to greater degree of variability in the operating speed and the energy consumption of the digital circuit. Therefore, the topic for today's video, we will be looking at the effect of all kinds of major variations and how it causes our digital circuit to deviate from its anticipated or specified performance. So our performance measures are how fast the circuit operates, that is the delay of the logic circuit, as well as how much energy is consumed. So there are two concepts I'd like to highlight and distinguish. One is the concept of variability, and one is the concept of reliability. When we talk about variability, we are talking about performance differences between individual units. So if you fabricate one integrated circuit, and then another exact copy of the integrated circuit, the same design but fabricated on a different part of the die, these two dies themselves will have some variability, some differences in the delay and energy consumption, simply because of the manufacturing tolerances of the geometrical metals, the geometry itself, the geometrical shapes itself of the metal layers and the transistors themselves cannot be exactly reproduced between die to die, and also within a single die itself. If you have two adjacent transistors versus two transistors that are further apart on the same die, that is the same integrated circuit, you might even have some variability in that, right? The transistor gate length will not be exactly the same, even though you have specified in the front-end design that they're exactly at the same technology process, which means that in theory the gate lengths should be the same, but they're not, due to process variations. So this we refer to as process variations. That is the variability in individual dies or within a die due to the nature of the fabrication process, and this variability causes our integrated circuits, our logic gates, to have different kinds of delay. So bear in mind, these are exactly the same design circuits, exactly the same transistors according to the front-end IC design, but because of the process variability, the variability introduced by the process, these very same circuits will actually end up having a spread of delays. So if you will have best case circuits that actually have a minimum delay, and worst case circuits that actually have a maximum delay. Okay, and there are another class of variations that are introduced between integrated circuits, and that is due to differences in the operating condition of the circuit, the situation under which you operate the integrated circuit. So voltage may be applied differently on the circuit, but it's not really the small differences in supply voltage that really matter in this case. It's rather the dynamic changes in voltage as we actually switch from logic 1 to logic 0. So in digital circuits, they tend to be operating at least hundreds of megahertz, and nowadays in the gigahertz regime. So there are many switching operations. The transistors are switching on and off very rapidly, and these switching transients will actually induce inductive voltage drops across long wires, and they also might be due to IR drops, resistive drops over long wires, and these transient changes in voltage may also affect the delay. So if the voltage is sort of on the larger side, on the higher side, then of course transistors are a little bit faster, because a higher voltage gives more current, and more current is more drive strength, so the transistors can actually charge and discharge quicker. Whereas if the voltage transients actually drop the supply voltage, or the voltage seen across the logic gate to a lower level, of course you will see a corresponding increase in the delay of a very same circuit and the very same die, but if it's operated in a different fashion, the voltage changes, you will see a spread in delay. Thirdly, also you will see this effect in operating conditions due to temperature. So when you first start up a chip and it's kind of cool, of course at lower temperatures, cooler temperatures, the transistors actually switch faster. This is because at higher temperatures, the carrier mobility, the free carriers, the electrons and holes in the transistor actually has reduced mobility at higher temperatures. So at higher temperatures, the speed of the transistor actually decreases. So variability, to summarize again, refers to the inter-die differences due to fabrication tolerances, slight differences in the fabrication, the fabricated geometry, or due to the differences in voltage and temperature operating conditions of the circuit. Whereas when we talk about reliability, we are talking about consistent performance, consistent speed, consistent temperature over time for one particular integrated circuit, for one particular device. And here we see that in modern VLSI integrated circuits, the performance of that same integrated circuit, that same die, will change over time due to effects known as aging. So there is a degradation mechanism called as aging, which actually degrades the performance of your integrated circuit over time. And these aging effects have become more prominent as we have scaled down the dimensions and the voltage of the digital circuits. So in this session, we'll go into more detail on the sources of variability as well as the sources of reliability, and be introduced to some statistical concepts of how we can estimate the effect of variability on the speed and energy consumption of VLSI circuits. So process variations will although a transistor, a logic gate, is designed for a particular width and a particular length, process variations will cause these widths and lengths to not be exactly the same for between dies, or even within the same die, even though it's for the exact same design. And of course, nowadays the oxide thickness, the thickness of the gate oxide to the channel is also something that varies quite a lot, as well as the channel doping, because now we are talking about 12 nanometer, 7 nanometer transistors. So the number of dopant atoms required to have a heavily doped N well or P well, you can actually count the number of dopant atoms on your fingers. So even a small deviation, like say you reduce one dopant atom, this would cause a large change in the percent dopant profile of the transistor. And of course, it's not just the transistors making up the logic gates that suffer from this process variation. Process variation also affects the dimensions of the wires, the interconnects that are routed over one transistor or one logic gate to another. So the dimensions of the wires may also change in terms of width, length, and thickness. Now, these physical parameter variations lead to electrical parameter variations, and the electrical parameter variations are what really causes the deviations in performance specification. Specifically, the physical parameters will change the current of the logic gates. So if you actually have physical variations that cause a reduction in current, the gates will operate slower, but of course the energy consumption might be reduced. Whereas if the physical parameter variations cause a larger saturation current, you actually have a speed up of the devices, but increase energy consumption. And it's not just saturation current that gets affected. The gate capacitance will also get affected, because gate capacitance is dependent on the area, the width and the length of the transistor. Another important parameter which also varies in a non-linear manner is the threshold voltage. That is the voltage at which the minimum voltage on the gate, which allows the transistor to establish a channel and turn on to be conducting mode. So changes in the threshold voltage, you would imagine, would definitely change the current, would definitely change the leakage current, and would definitely change the speed at which the transistor can be switched on or switched off. And of course, the wire resistance and capacitance will also be changed, because resistance and capacitance of the wire is also dependent on the physical geometry of the wire. And this definitely changes, as we've discussed, the gate delay, the wire delay, that is the delay in switching the gate or delay in propagating the charges and the signal across the wire from one output of one gate to the input of another gate. The slew rate will change, and this is the speed at which the inputs and the outputs of a gate can change. What is the rate of change, let's say going from a logic 0 to logic 1. And besides speed, energy consumption can also change. And what is the most significant change due to variability is really the leakage current. That is the current flowing from the source to the drain of the transistor when there is a zero voltage, when there is no channel established by a gate voltage across the transistor. So the transistor is theoretically supposed to be off, but because you have a non-zero voltage applied, this is supply voltage applied across the drain to source, there is a small amount of current that is flowing, and this is the leakage current, and this is what contributes to the heating and the significant part of the losses of a digital circuit. So in summary, physical variations, that is variations in the actual dimensions of the geometrical features in a digital circuit, cause electrical parameter variations in the transistors and transistors and the wires, and this leads to variations in delay and energy consumption. And the reason we need to consider these variations is because typically in a manufacturing process, although you've designed your VLSI circuit to achieve a particular specification, there is a certain percentage of the fabricated or manufactured dies that will meet these specifications, and certain percentage that will be outperform, and certain percentage that will underperform to the extent that they may not be acceptable to the customer. So it's important for a VLSI engineer to understand the range of delay and energy variations that will emerge from a particular fabrication process due to the design, and to be able to anticipate whether a certain percentage of this will be acceptable or not to the customer. So typically, to understand this range of variations, simulations during the verification step are run in what we call process voltage and temperature, or PVT corners. So you would not only simulate the performance of your circuit under expected operating conditions, that is the T corner. So this is, let's say, for a 1.8 voltage process, it's typically assumed to be operating at about 70 degrees Celsius, and typical NMOS and PMOS width and length. So if you're talking about a 5T process corner, this is actually the default average anticipated performance of a typical, this is like the ideal performance if there are no process voltage and temperature variations. Okay, so there are 5 alphabets indicating the process variation that affects the NMOS transistors, variations affecting the PMOS transistors, process variations affecting the wires, operating variations affecting the supply voltage, and operating variations affecting the temperature. So there are 3 possible corners at which you can simulate each of these parameters. The fast corner is the situation which leads to faster circuit operation. The slow corner is or S is the situation that leads to a slower circuit operation. So for instance, a fast NMOS corner is those variations that cause the width and length and the threshold voltage and the current to actually be higher, so that the transistor actually performs faster. And typically the fast corner, the F corner, there is a pre-specified process conditions where the majority of the transistors, some percentage of the transistors will actually hit that. So the simulations should be run with permutations or combinations of different process corners for all the NMOS, PMOS, wire, voltage, and temperature. So typically, if you are looking at meeting timing specification in the worst case, you would simulate at the TTT corner, that means like typical process corners, but in the worst case voltage, worst case temperature, operating temperature situation. So this is just looking at variations in operating conditions, so that you can do bin parts. And if you want to find the worst case performance of the circuit, you'd actually simulate for the 5S corner, that is the slowest of all the 5 dimensions of variability. And if you actually are investigating race mode failures, that is failures of the flip-flop to actually capture the correct values at one cycle, because the values arrive too quickly and do not respect the whole time of the flip-flops, you would simulate at the fastest corner. So the key takeaway point from this is simulations and verification and design verification at the front end stage are not only done at the default or anticipated mean operating conditions. They must be simulated for different process, voltage, and temperature corners. These are called PVT corners, to see that if the product, the IC, is actually operated under different operating conditions or goes through certain variations in the process during manufacturing, there is a high percentage of the fabricated products that would still meet customer specification. So the PVT simulations give you a guidance to help you to over-design your product, your digital IC, so that the majority of the parts would still be meet customer specifications. So let's talk a little bit more specifically about, in more detail about where the process variations arise. There are systematic variations and non-systematic or random variations that can arise. Okay, and the systematic variations typically arise from maybe lithographic patterns. That is, perhaps if you have certain structures that you place close together, in the circuit, let's say like for SRAM or maybe for array of flip-flops, if you place them close together, and somehow the lithographic system is not able to etch or pattern that geometry accurately. And the way you would actually address systematic variations, if you look at the resolution enhancement techniques for lithography. So these are systematic variations. The random variations, non-systematic, these tend to be more of just discrete fluctuations in maybe atomic differences, kind of fluctuations that arise, and they could be changes from die to die or changes within the die. So die to die, as you are aware, ICs are fabricated on a large wafer. So typically they're 8-inch wafers and 12-inch wafers, and now industry is trying to go to 20-inch wafers, and chips that are ICs that are in the middle of the wafer versus at the edge of the wafer typically have different performance because of the flatness of the wafer, and then differences in the mask and the light uniformity for lithography across the entire wafer. So these refer to die-to-die variations, and die-to-die variations are a little bit simpler to handle because you could typically characterize individual dies. That is, a die is actually just a single product, right? A single IC. So if you have the whole wafer, you could actually characterize the dies at certain parts where they are faster. So you could sell this as a faster or higher spec device versus the dies maybe at the edges that tend to have poorer performance. You could actually sell them as a lower spec device. So this is actually referred to as binning. So binning allows you, although it's the same design, but because of performance differences arising from the process variations between dies, you actually can use a marketing strategy to solve this, to actually sell products at different specifications. And this graph actually illustrates for one particular design, the statistical distribution of die-to-die variation in normalized leakage. This is the energy dimension, and normalized frequency, and this is the delay dimension. So we see that maybe for a typical die-to-die variation, you might see approximately a 30% spread variation in the operating speed of the VLSI IC. And this is for the same design, meaning that all of these dies are designed to operate at the same operating speed, and your front-end design is giving you a magic number from the max delay, that this is the maximum operating speed. But after fabrication, the process variations would lead to a 30% variation in the achieved operating speed. And what's more surprising is the leakage current does not varies more broadly, more largely. There is a 20 times variation in the leakage current. So meaning to say that the process variation for the exact same design will lead to one particular IC maybe having 20 times the leakage current versus another device. And this actually translates, if you look at I²R losses, this translates to a 400 times difference in leakage power consumption. Of course, this is a statistical distribution. You probably have way more parts at near the mean, but the fact remains that you actually have a larger variability in energy consumption, leakage energy consumption through the normalized leakage current, and you have some variability in the delay. So die-to-die variations are not insignificant. They are quite significant. And today, in modern technologies where the process we are going towards smaller feature sizes, a smaller transistor length, and correspondingly lower voltages in order to achieve higher speed. The within die variations, that is the variations in performance of transistors on the same die, but on one end to the other end, these have become quite important, and because they become quite significant. And let us first talk about, there are two kinds of within die variations. That are those that are spatially correlated, and these tend to be variations that arise from highly patterned structures. So you can think about them as maybe the decoder logic in maybe SRAM circuits or RAM circuits, okay, the digital decoder logic, or maybe any kind of very repeated regular structures, this could tend to suffer from spatially correlated variations. So these variations could be corrected by having a more uniform or changing the local pattern of uh, um, geometries, right? So this could be a layout or a placement or routing fixes that could change that could improve the spatially correlated errors. What we are more concerned about to try to characterize, because this typically is out of the designer's control, the independent random variations within a die. And there are three major variations that we have to consider. That is the random dopant fluctuations. This is, as I mentioned before, because the transistor sizes are so small now, the order of nanometers, and you can literally count the number of dopant atoms to generate a heavily doped N-well or heavily doped P-well. So one changes in one dopant atom changes would lead to significant deviation, and the standard deviation of the random dopant fluctuations would actually lead to variability in the threshold voltage, and the standard deviation is of this variability is dependent on the oxide capacitance as well as the width to length, the square root of the width to length. So as we scale down the transistor lengths, process technology for more advanced process technologies, transistor lengths goes down, the standard deviation of the threshold voltage increases by the inverse of the square root of the length. The second independent within die variation is the line edge roughness. That is, if you are actually building the transistor gate this side, the actual boundaries of the gate contact itself, it's not a straight line. It's going to fluctuate because of this little area is so small that you can count the number of atoms that make this gate area, this gate surface, and the line edges themselves are no longer straight, they fluctuate. So line edge roughness is inversely proportional to the square root of the transistor width. And the third dimension of variability, random independent variability, is the thickness of the oxide. That is the oxide between the gate, sometimes called the dielectric, and the channel. And in modern process technologies, we are down to 1.2 to 1.5 nanometer oxide thickness. So you can imagine that the accuracy at which we can deposit atoms, dielectric silicon oxide atoms to form this oxide layer, it's pretty, we are kind of limited in our ability to control the exact thickness, because we're at the level of controlling the exact number of atoms that we can deposit on the oxide. Okay, and this graph actually shows the trend of relative importance of these three independent random die-to-die variations as we go towards smaller and more advanced technology nodes. That is, as we shrink the transistor lengths. In the 45 nanometer process technology, the random dopant fluctuations actually contribute, that's this red line here, they actually contribute the majority of the threshold voltage variability. But nowadays, with 12 nanometer technologies and beyond, the line edge roughness, this blue one, is the dominant source of threshold voltage variability. We will continue on, we will end by actually describing in very briefly what is the source of this process variability. So here there's a schematic diagram of the NMOS and PMOS transistors, and they are no longer just your simple N-well, P-well, and gate devices. There's a lot of device level engineering, especially at the gates, in order to give you ultra thin gate oxides using high K dielectrics. These are dielectrics that are strained, so they actually undergo mechanical stress, and there's also some engineering on the depletion region of the polysilicon, and some work function engineering to actually control the interface properties between the gate contact and the actual dielectric and the actual channel. And of course, within the domain of the channel, you have a lot of interesting dopant profiles here: the halo doping, the shallow trench isolation, annealing, and additional strain engineering, and of course the channels themselves are non-uniformly doped with low diffusivity impurities, and again strain engineering to actually allow you to control the threshold voltage. All these advanced device designs only make the variability challenge worse for advanced process technologies. Okay, in the next video, we will further this. We'll come back to the main point, that variability, as you can see, the process variability explained just now, affects threshold voltage, and that in turn affects speeds. And we will discuss then in the future video the effects of voltage and temperature.